Hello. Today we're going to talk about what some of the graphs of enzyme inhibition might look like. First of all, what we got to do is look at our normal enzymatic reaction. Normally, substrate binds to an enzyme and is converted to product. What this might look like if we graphed it is this. We look at velocity versus substrate concentration. We notice that as the substrate concentration increases, our velocity tends to level off. In other words, we reach a maximal velocity. We talk about saturating all the active sites with substrate at this point. We can also plot the enzymatic kinetics using what's called a double reciprocal plot, which is shown at the bottom here. This is also known as a Lineweaver-Burk plot. At lower concentrations, so down in this area of our initial plot, it's very linear. So we can plot this linear function using this double reciprocal plot. A couple things to note on this plot. This point here, in other words, the y-intercept, is also known as 1 over Vmax. Okay, so this is essentially the reciprocal of our maximal velocity. Another term that we'll talk about is our x-intercept. This is negative 1 over Km. We'll talk about what Km is in a later video. So let's take a look at some of our different types of inhibition. Competitive inhibition. So remember, in competitive inhibition, an inhibitor is going to mimic what the substrate looks like. It's going to make sure that it's going to bind at the same place as the substrate, and it's going to make sure that the substrate does not get turned over. So if we think about this, if we keep adding more and more substrate, we might be able to compete out the competitive inhibitor and get back to our maximal velocity. So let's take a look at what this looks like on a graph. What I've shown here in red is our normal enzymatic activity. And if we put in an inhibitor, which is going to be the dashed line now, we see that eventually, if we add enough substrate, we will get back up to this maximal velocity if we add enough substrate to compete it out. If we look at our Lineweaver-Burk plot or our double reciprocal plot, we can see that, remember this intercept here, our y-intercept is 1 over Vmax. So our maximal velocity did not change. And so we'd expect that our maximal velocity is probably not going to change when we add an inhibitor. And that's exactly what we see. In fact, we see a plot, again, the dashed line is with our inhibitor, passes through the same y-intercept. However, at the bottom here, on the x-intercept, our Km value increases. In other words, our negative 1 over Km gets closer to 0. Let's take a look at uncompetitive inhibition. Uncompetitive inhibition is when the inhibitor can bind only to the enzyme substrate complex, thus inhibiting it. When the uncompetitive inhibitor binds to the ES complex, the enzyme can no longer function as it could in the absence of the inhibitor. So the Vmax rate will decrease. If we think of Le Chatelier's principle, the equilibrium is kind of shifted as the ES complex is removed. So we're removing it and placing it with the inhibitor here. And this will push the equilibrium towards the ES complex, so more formation of this complex. If that's the case, then we might see an initial burst in activity. Let's take a look at what these graphs might look like with uncompetitive inhibition. Again, the red is showing normal without an inhibitor present. Okay, we predicted that the Vmax would decrease for this, and then we might see an initial burst. So what does it look like? Our dashed line is with our inhibitor. We see that we don't reach the same maximal velocity. We don't reach that red line up there, and we see an initial burst to begin with. What this looks like on our double reciprocal plot, we see that our Km has changed, okay? Our Vmax has changed. Our Vmax up here was lower, so our 1 over Vmax should be a little bit bigger. Our Km has also changed. One way to tell that you have uncompetitive inhibition is when you plot inhibitor concentrations with activity versus no inhibitor, so normal activity. You'll get two parallel lines. Finally, let's look at non-competitive inhibition or mixed inhibition. Remember, this is when the inhibitor can bind to either the enzyme initially, or it can bind to the ES complex, okay, to take them out of action. Again, binding at either of these places will take and decrease the maximal velocity as compared to when there is no inhibitor present. But since both forms can bind the same amount of substrate as was shown in initially, we wouldn't expect the Km to change. So let's look at these two plots. Again, the red is without inhibitor. Let's look at what would happen in our initial one. So when we plot velocity versus substrate, we see that our Vmax is decreased. We'll talk about how we determine Km from these plots, but Km is very similar. In our double reciprocal or Michaelis-Menten plot, when we put our inhibitor data in there, we see that our y-intercept, or 1 over Vmax, has changed. Remember, it was decreased here, so it means our reciprocal of that is going to be a bigger number. And our Km is the same. So in non-competitive inhibition, we're looking for a line that has the same x-intercept, but a different y-intercept. All right, hopefully this will help you when determining what type of inhibition you have by quickly plotting a Lineweaver-Burk of your data.